Okay, it's 2:30, so I appreciate you guys being punctual and early, so I'll go ahead and get started. My name is Bernardo Malficana. My website is understandingairplanes.com, and most of what I do I put on my website. So you can go to that website, and there's a resources tab where you can download all the presentations I give, you can download all these slides. So it's all up on the internet. Don't feel like you need to take notes or record things or take pictures. Of course, you're welcome to obviously take all the pictures you want. I'm recording the video in the back there, so hopefully I'll put this all up when I get home. A little bit about myself, or why you should listen to me when I talk about 3D printing. I have a couple of fancy mechanical engineering degrees. I've been an airplane geek my whole life, as I'm sure have most of you. I'm a pro on Arc 6, I enjoy it very much. Long story short, I'm a construction engineer at one of the large airplane manufacturing companies. And on the side, I created and teach this course that I call Understanding Airplanes. So that's what I do a website for it. And just to give you a little bit of the background about where that came from, if you're into airplanes and you're a kid, you probably have all these questions about how airplanes work. And, why is it that the horizontal stabilizer pushes down, and why aren't more airplanes combat airplanes or flying wings, and why don't we have more electric airplanes, and why do small airplanes seem to have propellers and large airplanes seem to have jets, and how do winglets work, and those kinds of things. And so I always wanted those things, and then I went to college and I studied engineering, and I learned the answers to these questions. And unfortunately, they're buried behind these thick textbooks full of intimidating equations. So what I thought I'd do is create a course for people who aren't engineers and who don't want to go look for engineering textbooks to explain how airplanes work and these things. And so I do that on the side. And actually, once I started working with Boeing or afterwards, I started teaching this course at Boeing. There's the course that I created outside. There's huge demand, right? So a lot of people at Boeing are not airplane people. There's a lot of people at Boeing who are, accountants or HR people or communications people and so on. Even among engineers, right? I'm an engineer, and I'm a structures engineer. So I work on one side of me sits a material scientist, and on the other side of me sits a guy who has a civil engineering background, right? They don't know a flap from an aileron unless, we tell them. So I created this Airplanes 101 course. So a lot of what I do publicly for fun and put on that website on understandingairplanes.com comes from these kind of for fun, how do airplanes work kind of thing. And these things are 100% public, right? I should mention that, I'm going to give you a lot of specifics about a lot of 3D printed parts out there in the industry. But all that I'm going to say is 100% public. At the end of these slides, I actually list the URL where each image comes from and where each fact comes from. So you can go read more about any of the things I'm talking about. So what we're going to talk about, 3D printing technologies, how they work. I'll give you a survey of aerospace applications, so lots and lots of 3D printed parts on airplanes, it's on the Spacecraft. And then I'll talk about what's the current research going on to make, what's the next step in 3D printing, what are people trying to do to get there. And I should probably specify that this isn't really 3D printing for home builders, because I'm mostly going to talk about more advanced technologies and more expensive 3D printers than most individuals have. I'm going to talk about 3D printers that can print metal parts that cost millions of dollars. But I will have some resources at the end, so that if you as a home builder want to learn more about what you can do at home and what you can do in an airplane, you can go look at those resources. But what I want to tell you about today is what's happening in the industry, right? What's Boeing doing, what's Airbus doing, what's Lockheed doing, so that you can kind of be inspired and think that, maybe someday this is something you can do for home builds, or maybe there's a way for your creative to apply some of this to home builds, or something like that. I think that's all. So, 3D printing, also known as additive manufacturing, the general idea is that you print things one layer at a time. So you have a printer that creates one layer of the object, and then on top of it, another layer, then on top of it, another layer, and so on. And once you have enough layers, you have a 3D shape. There's a few different technologies that I'll talk about. There's a few more. What I'm going to focus on are stereolithography, which works for plastics, fused filament deposition, which works for plastic, and that's the one that most hobbyists use. And there's also powder bed and selective-sintering, which works for metal or plastics. And then there's plasma deposition, plasma spray, that works for metals. So I'll explain to you briefly how these things work, and then I'll talk about how we use it in the industry. All right, so stereolithography, that's the first one. That's the original form of 3D printing. It was invented in the 80s. And what it is you basically have a pool of resin, kind of like the resin using, in easy, that's cured locally by laser light or by UV light. So imagine just a bucket of goo and a projector, and that project like the projector on the screen. And if that projector projects a shape on the surface of that goo, that shape will cure, will harden, and become a solid layer of plastic. And then if you cover that up with goo, you can print another, solidify another layer, and then cover that up with goo, solidify another layer, and so on. And you have to, lower the object each time and recover it with goo. So I'm going to show you a video to illustrate what I mean. So here's a bucket of goo. There's something solid in there. You have that plate kind of covered with a thin material. There's the light to cure it. Another layer. Sweep across again to make sure it's a thin, nice thin layer of resin. And then the light again. Once it's the right height. You do this a whole bunch of times, and layer by layer, you end up making some kind of 3D object. And of all the techniques I'm going to talk about today, this is the only one that works at room temperatures. Most of the other ones require the material to be melted and solidified, so it ends up being really hot. But this one, because it's curing, this is a chemical reaction, you can do it at room temperature. Here's another one. So make a little Formula 1 car. This one's speed it up here. Then you just cover with a layer of goo, shoot the next layer, and end up with something like that. There's different ways to do it. You can also raise the object up out of the goo and cure the bottom. So we're using the light of the tower and raising it up layer by layer. So that's stereolithography, and that's how it works. The other kind of classic 3D printing I'm talking about is fused filament fabrication, and that works kind of like cake icing. There's a nozzle that squirts out basically something like hot glue that as it comes out it solidifies. And there's a filament, there's a little wire that goes into that nozzle that's heated locally and squirted out. So if you buy a 3D printer, this is probably going to be how it works. And then, so I'll talk about powder bed technologies. And these can work for metal, and they also work for plastic. If you get something from Shapers or something, they'll probably use the plastic powder bed method. And this is very similar to the goo kind of approach, where you have a bucket of stuff and a beam that comes down from the top that solidifies it, but instead of a goo, you have a powder. So you have a container. You have a container for powder, your laser or your electron beam or whatever melts the stuff on the surface, solidifies it into a layer, you cover it up with more powder, melt it again. The key, and I'm going to get into the pros and cons, and let's say you're making airplane parts, what do you think about? For the powder bed, you can make relatively small, fine details. You can make, very, relatively smooth surfaces. But the maximum size of the object you can print is the size of the powder bed container. So if you want to print something huge, you would need a huge container of powder. That starts getting expensive. Show a quick video. So covering it with powder, you can see the laser kind of scans back and forth, and there's different patterns and directions you do with the laser. Powder, layer, powder, layer, powder, layer. This is obviously a kind of cartoonish. Here's what it actually looks like. So that's one layer, and a fresh layer of powder. Print another layer of the object. And this is a titanium, by the way, so you can do this with, we can make real airplane parts like this. The surfaces are a little rough, so usually you have to polish them. That's what I'm talking about. And finally, let's talk about direct metal deposition. So in a way, that's analogous to the fused filament, where you have a little nozzle that squirts out molten metal, and then the nozzle moves around and deposits the molten metal as you go. So if you have another nozzle, you eject it. The key advantages is that, so the nozzle that sprays out hot metal is at the end of some robotic arm, right? Something that can carry it around. So the size of your part is limited by the motion of the robot. So with this kind of metal deposition, if you have a robot with a lot of movement range, you can make a large thing. But the disadvantage is that the surfaces are relatively rough, and you can't make small, fine details. So here's a video. Should try to synchronize playing the videos with the F-22 phone, but it doesn't quite work. So the little nozzle is basically ejecting really hot, titanium, or sometimes it's aluminum. I'll tell you why we mostly do titanium and not so much aluminum in a second. So again, you're basically making layer by layer. This is like a turbine blade in a jet engine. And the surface is very rough, so you do have to polish it. So that's the kind of thing I'm talking about when I'm saying, 3D printed metals. Okay, so we have this technology, we can make stuff like this. What are the pros and cons? The pro that you always hear people talk about with 3D printing is complexity is free, right? Because you have, usually to make a part that has a very complex shape, lots of details, it takes a lot of work. But if you have a robot printing the part, it doesn't really take that much more time or work or expense to make a very complicated shaped part rather than a simple shaped part. Although, that's only if the surfaces don't have to be smooth. You have to go and smooth all the surfaces afterwards, and complexity is definitely not free. Another pro is that there are no tooling costs. So to make most kinds of parts, you usually make a mold or a mandrel or a form or some kind of tool that makes it easy for you to shape sheet metal or lay down composite or whatever. With the 3D printer, you just need a 3D printer and it just spits out the part. So that's an advantage. Lead times are shorter, in part because you don't have to build the tool. And you waste very little material. Excuse me, you waste very little material. You're not machining away at a piece of metal and making chips everywhere. You're just using the metal that you need. But the disadvantage is that each item is more expensive than if you made it using conventional means. And I'll get more into that in a second. Usually the 3D printed material isn't quite as good as normal materials, as rock materials, as molded materials. Usually you end up with materials that are lower strength, that have more porosity, more inclusions and imperfections, worse durability. Like for example, most of you guys probably know that welding is tricky, and when you make a weld, there's a higher chance of there being imperfections in it, and like fatigue and so on. But when you 3D print something, the whole object is a giant weld, right? So that kind of gets across the idea that the material is not going to be super great. Surfaces tend to be rough. A lot of times when you 3D print something that has overhangs, so imagine making a little model airplane with cantilever wings, while you're printing it, the wings will kind of droop. So usually you have to 3D print some scaffolding underneath it just temporarily to hold up the model while it's being printed. And the material properties are highly process sensitive. Right? The material properties of the 3D printed stuff depend very much on whether the 3D printing is fast or slow, or if it was a hot day or a cold day, or if the object was oriented like this in the printer or like this. And there's all these little details that will influence the material properties. And if you're just making a model to sit at your desk, that's fine. But if you're making an airplane part that's going to take stresses and temperatures and vibration and so on, then you really care about the material properties. And then I talked about the cost situation. The cost situation. So in a traditionally manufactured part, say you make a tool or you make some kind of machine to make the part, if you only make a few parts, each of them is going to be very expensive because you have to pay for the cost of the tool with just a few parts. But then if you have a tool that makes parts quick, as you make more and more and more parts, they get really, really cheap. Right? To make each one of them is pretty cheap. With a 3D printer, once you have a 3D printer, each part basically has the same cost. So, and what that generally means is that if you're going to make only a few parts, then 3D printing probably is more likely to make sense. If you're going to make a large number of parts, it probably makes more sense to use traditional methods. And it's just like homebuilt, right? If I say I'm going to launch a kit of this airplane I designed, I'm probably going to make molds, right? And have other forms or other tools to make parts. But if I'm just myself at home and I want to build one airplane, like let's say a Canard airplane, it probably makes more sense to make foam cores and wrap them with fiberglass. And I'm going to build it differently than if I wanted to build hundreds of them, right? So the same thing applies to 3D printing. 3D printing makes a lot of sense if you're making a few things, but if you're going to make a whole lot of these things, usually it'll make sense to have a mold or a dedicated machine. Okay, so that's the theory or the background. So let's talk about aerospace applications. What's going on in the industry? So I'll talk about models, so display models, wind tunnel models. I'll talk about parts used in flight tests. I'll talk about tooling used in the factory. And, each of you guys is a small airplane factory, so you'd be interested in the uses of 3D printing in the big airplane factories. And then I'm going to talk about actual airplane parts. I'll talk about air ducts, and engine parts, and spare parts, and there's UAVs that use all kinds of parts of 3D printing. And then I'll talk about spacecraft, and I'll finish by talking about structure. So like I said, I'm a structures engineer, and that's the part that I really spend the most time thinking about. So as you know, it's fairly easy to 3D print a display model. And display models aren't just decorative. A lot of companies use models to figure out the layout of the factory, or figure out if it's really possible to put these parts together, if they all fit in each other, and all those kinds of things. So you can 3D print display models. That's been done for a long time. You can 3D print wind tunnel models, right? So Lockheed 3D printed some of the F-22 wind tunnel models using stereolithography in the 90s. So that goes way back. So that's Robert Bailey. He won awards in the 90s for being innovative with 3D printing and making those F-22 wind tunnel models. And a stereolithography, because it's a cured resin, oftentimes ends up looking kind of clear. You can kind of see light through it. So typically when you make something out of stereolithography, it looks kind of like that. It looks kind of like amber or hot glue or something like that. Try to find some more recent examples. I don't know if you know about the Aurora D8, which is an airliner that uses a boundary layer injection. So they put the engine, they have like a V-tail with a jet engine between the V-tail, sucking in the air right over the fuselage. So one of the wind tunnel models is 3D printed. The wing right here is someone who's doing research on the effects of icing on swept wings, so what are the aerodynamics of icing, so they 3D printed some wings and some icing. I don't know if you've seen pictures of the Eurofighter Typhoon flying around with conformal fuel tanks. So that's one of the wind tunnel tests, and they 3D printed them all. Oops, there's text. And oftentimes, airplane manufacturers will 3D print things to do fit validation. So they design a part, they have an airplane or an assembly, and they want to make sure that the part fits. Oftentimes, it's cheaper to 3D print a part of their proposed design and then go there and put it in and make sure you can actually put it in, rather than engineer the part and go in and see it doesn't fit and have to go change all over again, and it takes time. And I've heard people from Boeing have published articles saying, quantifying how much money it saves them to when they design a new part for an old airplane to make sure you 3D print it first and make sure it fits, because that will catch errors much more quickly and cheaply than the traditional one. So that's a helicopter rotor hub. This is the fitting for the camera in the A380. I don't know if you fold in the A380, but it has a camera on the tip of the vertical stabilizer, so you can see the video of the airplane thing. So they 3D printed the housing for the camera and stuck it in there to make sure it fit. And this is, I forget if this is the A330neo or the Wingbo. It's one of the new Airbus airplanes, and they were making a newer, bigger ECS stuff, like air conditioning system stuff, and they 3D printed one and put it in the airplane and make sure it fits. This is a Vector. They have a booth right here. My first flight training was on the Vector Sports Star. I really enjoyed it. And when they flight test new things, they 3D printed, pitot tube fairings and wing to body fairings and some interior stuff and cooling grills and various things like that. Because when you 3D print something, it's probably not going to be as durable as if you made it using traditional processes, and it's probably going to be a little heavier. But if you're just flight testing the aerodynamics of something, that doesn't matter. So you can 3D print things for flight tests. They're trying to do drag reduction studies on the C-17 and also the C-130. So they've actually 3D printed these drag reduction things and then stuck them on C-17s and on flying and see if they change the airflow the way that they intended. When you're certifying an airplane for a flight into no icing, you have to do some kind of analysis or simulation or testing to make sure that the wing generates a certain amount of lift with ice on it. And one thing you can do is 3D print ice shapes and stick them on the wing and go fine. So now you don't rely on you don't need actually icing conditions to do a flight test. And you can 3D print kind of a worst case scenario part, right? If you just rely on nature, maybe you won't get the icing that's like the worst case icing. Then the FAA may be like, it could have been worse. I don't know if I believe that test. But if you 3D print really bad icing, you stick it on the wing, and if the airplane flies okay, then you're good. The A330neo flew recently for the first time. That's an A330 with new engines and a few other little tweaks. And as you may know, when Airbus or Boeing test fly a new airliner, they're not 100% sure that the static ports are picking up the full static pressure, so they have a static pressure system in that little cone that hangs off the tip of the vertical stabilizer. And there's a tube that goes into the airplane and has a reel, right? So they unreel the static cone off the back. And they 3D printed a bunch of the things related to that system on the A330neo. So basically have that sticking up on top of the wing and a bunch of these parts are 3D printed. So another flight test example. Airbus was recently testing a helicopter with a new windshield wiper mechanism, and they 3D printed that during the flight test to make sure it worked. So that's enough for flight tests. The main use of 3D printing in the aeronautical industry is in the factory. If you go to Boeing and Airbus and Lockheed and SpaceX and so on, sure, they 3D print some actual parts, but most of what they 3D print is actually stuff in the factory to, protect corners of things. So people don't bump and hurt themselves. Little holders for tools that you kind of hang on the thing you're working on, or little, holders for little bits. Basically 3D print yourself a custom toolbox that just needs to be, the order that makes makes the most sense to you, and so on. So if you go in the factory, all kinds of manufacturing assembly people are always inventing little 3D printed parts developing in the factory. They 3D print jigs to hold the parts in place, all the parts are assembled. They 3D print these check form, they 3D print a part that if once you assemble something, you can take a 3D printed part and put it up against it and make sure you actually assembled it right. If it's wiggling or if it's too tight or something, then you didn't assemble it correctly. Drill guys got the drill holes in certain places, you just 3D print a strip and put it on there and it has the holes in the right place. I don't know what the details are here, but apparently T-38s are getting new floors, and they 3D printed a jig to, bend the metal and put the floors together. So again, all kinds of factory type uses for 3D printed tools and jigs and holders and wiring guides and things like that. And also molds, right? You guys know that they can mold. Most of you guys probably know that they can mold. You 3D print your mold, and it's made and it's ready, and you can put your fiberglass or your carbon fiber over it and your parts. So some of these are for the so-called manufacturing jet. In tooling, the largest 3D printed object tool right now is a tool for the 777X window. I'll let you watch this. So this is giant. This is like, I don't know, 20 feet long or something like that. And there's a picture of the Guinness World Records guy measuring it and saying, yes, this is the largest tool. And it's 3D printing it upside down. That's the bottom right there. I'll let it play again so you can see what I'm talking about. That's just kind of structural. So again, this is a curved surface with the wing, goes in, and there's stuff in it. I'm not 100% sure, but if you Google that, you can find it. They've published quite a bit about it. It's some kind of plastic. Now, I don't know if you've seen this video of the Harrier that the nose wheel got stuck up, and so the Marines put out this little maintenance stand out, and the pilot managed to land the Harrier with the nose on the stand. And that did a little bit of damage to one of the frames on the other side of the nose, as you might guess. And so they had to design a repair, which are those green and purple parts over there, to kind of bridge over the damaged frame. And so what they did is they 3D printed these plastic forms, the white things, so they put sheet aluminum on them and kind of bend them to the shape of the repair. And then they took them out of the 3D printed forms and they fit right on the Harrier. And this is a Northrop part, that there's a certain Northrop airplane, they don't specify what it is, but it keeps needing repairs in a certain area. This looks like the corner of a landing gear bay to me, it could be anything. But what they say is instead of having to basically take half the airplane apart and then crawl inside it and see what the damage is, and crawl back outside and design a repair and go back in and it doesn't quite fit, and it takes a long time, it's kind of error prone. Northrop 3D printed this thing, so that the mechanics can just create the repair on the thing, and once the repair is done, the repair part, they can then go in the airplane and install it, and it fits into the first time. So for a lot of repair applications, 3D printing a form and then creating your repair parts over that 3D printed form makes sense. Alright, so let's talk about actual airplane parts. We'll talk about flight tests, about factory stuff, about repairs, but what about actual parts flying on actual airplanes? Here's a quote for you. Boeing commercial airplanes are currently flying 25,000 actively manufactured parts. Each 777 is about 30, and this is a few years old, so the numbers are probably much higher now, but this is the kind of numbers we're talking about here. People often ask me, hey, when's Boeing going to start using 3D printing on its airplanes? I'm like, oh, we've been doing it for a long time, actually. And I'll show you the examples that Boeing has talked about. Not much Airbus and Lockheed ones too. Most of them are components like air ducts. So most of them are plastic SLS nylon air ducts, but there are some metal parts too. So let me show you a bunch of examples. Here's a whole bunch of air ducts. So the 787 has a bunch of 3D printed air ducts. The Bell 1409 has a bunch of 3D printed air ducts. The F-35 does too. The F-18, the newer F-18, the Super Hornet, has a lot of 3D printed air ducts. Most, I won't say most, but a whole lot of parts, in the order of 100 in each F-18 are 3D printed plastic air ducts. And you might look at it and go, oh, no, it's just an air duct. It doesn't even have to do anything. But an air duct in an F-18 has to handle a lot of G's, so it has to handle like several times its own weight, a lot of vibration, a lot of temperature, high temperature situations, and it's not as simple as just blocking air duct on airplanes. And that air duct has to survive a lot. And because 3D printing allows you to, I'll get more into this later, but 3D printing allows you to forms are more optimized. They actually ended up with lighter air ducts than the ones that were previously. So they not only are, they're saving weight on the F-18 by using 3D printed air ducts instead of the old ones. And there's a lot of little things like brackets and interior parts. So the A350 also has a bunch of air ducts. It also has a bunch of brackets. So things that hold the the air conditioning ducts and the edge of the seat on, things like that. So all of these up here are A350 parts. There's something like 500 in each A350. And then individual airlines will sometimes certify little brackets or interior bits to put in their airlines. So that's a CAD. 3D printed some of the frames that go around the screens in the cabin. And Air New Zealand 3D printed some of the little cup holders that flip down on business class and so on. So there's a bunch, and there's more and more of these interior parts because the certification requirements are not super harsh. And this kind of nylon is pretty good. Temperature resistance we're calling passes the flammability toxicity requirements. So if you can come up with something, you can probably put it on the airplane. More and more airlines are doing it. Engine parts. So engine companies love 3D printed parts. Most of the metal 3D printed parts that are actually flying on airplanes right now are engine parts. And the reason is that engine parts have very complicated shapes, a lot of them do, and they are usually made of lots of little parts that have to be machined to very tight tolerances and then assembled, usually by hand. So you need very tight tolerances, which is expensive. You need people to assemble them by hand, which is expensive. It takes time, and it's error prone. So if you can substitute all that by just a single 3D printed part, it kind of saves you a lot of expense and a lot of time. So the first one was the 777 compressor inlet temperature sensor housing. So using a 777. And both these are GE. And the other one was the fuel injection nozzles using the GE used on airplanes like the 737 MAX. And again, this used to be multiple parts that had to be machined to very tight tolerances and then assembled by hand. And both of those things are expensive and take time. So even though they're making lots and lots of these parts, it's easier to 3D print them. Boeing makes 50-some 737s a month, and trying to make even more. And there's like 19 of these per engine, so 38 per airplane. So you multiply out how much that adds up to. There's a whole lot of these. So every day they're going to make like 80 of these, and they have a whole bunch of 3D printers going full time, making these things. Because it's something like 80 a day, which is a lot. So here's with a hand to scale, so you can tell how big it is. It's like this big. Other things. In Korea, they had to replace the turbine casings on their F-15s, and they went from just buying the parts again and replacing parts to 3D printed titanium. This is the only one I was able to find public cost information about. And the cost of each of the turbine casings for the Korean F-15s went from $34,000 to $2,500, and the lead time was also decreased substantially. So it's much cheaper. The largest metal 3D printed part that's flying is a bearing housing on the latest version of the E350. So you're talking about a lot of engine parts because they're small, they have complicated shapes, and they can be very expensive to machine and assemble manually. So if you can make one 3D printed part that used to be lots of little parts, you save a lot of time, you save a lot of money. A clear example that GE is always bragging about is their Catalyst advanced turboprop. It's going to go on the Cessna Denali, and it's based on a previous engine, based on the CT7. And there are 900 parts on the CT7 that became 16 parts on the Catalyst engine because of 3D printing. And GE also has the T700 base engine called the T901. That one's going to go on the Black Hawk helicopter. And again, there's one part in the T901 that used to be 50 parts in the T700. So because of 3D printing, you can combine all these parts. And there's a lot of other examples too, if you Google around. These are European and Russian ones. So those are actually flying on actual production airplanes, but just to go back to demonstrators for just a second. There are companies that have made entire jet engines that are almost entirely 3D printed. I mean, they have little electronics and things in them. But other than that, they basically can 3D print an entire jet engine. Multiple labs and universities and NASA and so on have 3D printed jet engines entirely from scratch. And more of the space companies that I'll show you in a second, so SpaceX and so on, use a lot of 3D printed parts on rocket engines. Okay, so that one's NASA, that one's GE, that one is Monash University. They 3D printed an Aerospace engine, I think that's kind of cool. And then small spare parts, right? The A300 and A310 are very old airplanes, and the company that Airbus was working with to make, little seatbelt holders and things like that for the airplane doesn't exist anymore. And so when they need to replace those seatbelt holders, you know, do they go to a whole new company that's going to create tooling to make seatbelt holders, or they just 3D print them? So now they're 3D printing these spare parts. Or I don't know if you've heard about the Orbis DC-10, you know, it's a flying hospital thing, so they've replaced some of the air ducting with 3D printed parts. You know, DC-10's a pretty old airplane, and it's going to be hard to go back to the original suppliers from the 70s and, you know, ask for parts. You know, the Tornado is also getting kind of old, the Tornado fighter in Europe. And there's a few little things in the cockpit, like, you know, radio covers and throttle guards and little bits that you pull out before you go flying, that they're 3D printed during maintenance. And, you know, the US Air Force, right, so things like, you know, you got an armrest and there's a little plastic cap on the edge of the armrest so you don't scratch your hand with the edge of the aluminum. So yeah, they're now 3D printing the little caps to put on. But, you know, the general idea here is that all kinds of like little plastic bits that normally you have to go to a company that creates a tool and takes time, you know, now you can 3D print and people are. Let's talk about UAVs for just a second. So Airbus 3D printed the 4, all of it, so it's almost entirely 3D printed as a UAV. That's kind of cool, and it actually flew. There's a company called Aurora that worked with Stratasys, which is a 3D printing company, to 3D print the first jet UAV. It's almost entirely 3D printed. And I think it's kind of cool to look at the inside of the wing structure and see how it has a little, you know, little truss structure filling it up. So you know, if you think about like a foam core structure, like an easy wing or something, you know, the skin is really doing the work, and on the inside you have some foam that just kind of holds it in place. You can basically 3D print the foam by making that kind of lattice structure on the inside. That's pretty cool. And there's various UAVs. Like NASA took two UAVs, I forget what they were called, something high, and 3D printed new large wing and a few other parts, and combined the two UAVs into a single, much larger UAV that they call the Frankenhigh, and it has much more endurance, much more range, very more stuff. And all kinds of universities all over the place are 3D printing entire UAVs. Because once you get good at 3D printing, you can start asking yourself, you know, how do I design something to make it easy to 3D print? So you're learning how to design an airplane and learning how to design for manufacturability at the same time. So University of Virginia created one called the Razor UAV, and they made a little video about it. I'll just play for a minute or two here. So, you know, it's a really good quick summary of the whole process. Of, you know, you can design something on the computer, you can print it pretty quick. If you make some kind of mistake, you just make another one. You can 3D print winglets and ailerons, and it should all, you know, if you did it right, it all snaps together. Of course, the electronics and the engines you're not going to 3D print, but you can ideally just pop those in. You can end up with a little flying wing, and it works. So that's pretty cool. And I'll talk about, and then let's talk about spacecraft for a second. I can sit here all day and tell you about 3D printed parts on spacecraft. There's all kinds of satellites and things and rockets that have a lot of 3D printed parts. So, you know, some of the oxidizer valves and the SpaceX rockets use 3D printed parts. Some of the, you know, there are various Asian satellites that use, you know, antenna mounts that are these weird organic looking trusses that are 3D printed. You know, Boeing uses 3D printed aluminum parts on their satellites, and Lockheed uses 3D printed parts on Aerospace probes, so, you know, probes that go to Jupiter and that kind of stuff. And then there's CubeSats, right? I don't know how much you guys know about this, but if you Google CubeSat, there's this standard of satellite. A satellite has to be, you know, it's about 4 inches by 4 inches by 4 inches, and almost whatever you can fit in there, you know, within certain limitations, which you can buy. You can basically piggyback on a you know, on a real space launch, you know, a launch of a large satellite or space probe might have a few slots along the side so they can take up like 12 CubeSats or something. And then universities and other kind of low-budget research operations will buy one of the CubeSat slots and launch their CubeSats. So a lot of universities make CubeSats, and those are exactly the kind of thing where 3D printing makes a lot of sense. There's a lot of 3D printed CubeSat parts, so propulsion parts and little mechanical parts. So yeah. So again, I could talk about this all day. I'm not really a space person. I'm an airplane person. You guys are too. And you might look at these things and go, wow, oh yeah, well, they need to be very reliable or very high quality. These are, you know, these are unmanned. These spacecraft, if they fail, it's not a big deal. And I didn't appreciate how wrong that was until I started working on spacecraft. I worked for a year and a half on satellite control systems. And something that I didn't appreciate is that when you make a satellite and you launch it, especially a communication satellite, like for television stations or for telephony, that goes up into geostationary orbit, so 30,000 miles away, no human will ever touch that again, right? It's going to go off, or go off into Jupiter, or go off into orbit, and it has to work for 20 years, non-stop, without anyone touching it. Like, think about that level of reliability. It's really something. So these don't have to be, these can't be any crappy little thing. They actually have to be good prices. And you say, oh, but and they're not on the end, right? No, there's actually 3D printed parts in crewed spacecraft as well. So the seats in the Chinese spacecraft are 3D printed, and the what's called Starliner that Boeing is building has all kinds of 3D printed parts, and the Lockheed Orion has 3D printed. So there's a lot of 3D printed parts, especially in the newest generation of crewed spacecraft, of capsules. And here's a really neat thing, you may have heard about this, that they took a 3D printer to the International Space Station. And NASA on the ground designed a few little tools and belt buckles and things, and electronically transmitted the files to the International Space Station, and the astronauts in the station 3D printed, little objects. And that may seem like a novelty, but if you can 3D print, a zip tie or a clip that holds something together, or a wrench that's just the right shape to turn something around that's hard to reach or something like that, that's actually useful. It's actually pretty cool. Yeah, so that was the big question that they wanted to address is, does it work in zero-G? And this is a fused filament machine that they took up. And if you imagine a layer of material and the nozzles here supporting the next layer, the nozzle's close enough that the supported material basically hits the next layer right away. It's not really rapidly driven at all. And before they sent it up, on the ground, I think they showed that it works upside down and all that kind of stuff. But yeah, that's definitely the main question that comes up. There's something called relativity space, and they want to 3D print a whole rocket. And towards doing that, they created the largest 3D printer in the world. It's called a Stargate printer. And like I said, the size of the thing you print, if you're doing plasma deposition, is only limited by the range of motion of the robot that has a little nozzle at the tip. So they created this chamber with these robots with giant arms that can 3D print a whole rocket. And they've already 3D printed a whole fuel tank. It's about the size of a car. And they say that thanks to this capability, they can design and create the thing and test the thing and reiterate much more quickly than if they were relying on, external suppliers or even their own machine shop. So that's kind of cool. All right, so now let's get to what really matters here, home builds. So a lot of people, a lot of EAAers 3D print little parts for their airplanes. So I'll give you a tour of those, and these, of course, are going to probably be more applicable to you, and you can hopefully draw some inspiration from them. I don't know if you heard about the EMG6. It's an electric motor glider. They've done presentations at Oshkosh. I don't know if they're by the ultralights this year or not, but they have been in previous years. So they 3D print a lot of little fairings and things that go on. So all these great things, they are, right? See if this works. Should be able to point. There we go. So all these little gray things, this clip and this fairing, and the fairing they cover would take to make sure stay snug, are 3D printed. Multiple people have 3D printed air intakes for their Sonics airplanes, which is kind of cool. So as you can see, it's kind of a complicated part. To fabricate this would be complicated, to make a mold for this would be complicated. But if you 3D print it, you just pop the outlet printer, put it in the airplane. And again, it's one of those parts that, if it fails, it's not a risk to the safety of flight. So you can 3D print it and not worry about it. There's a lot of 3D printed RV parts. If you go on Vans Air Force and you search for 3D printed or 3D even, you'll find gobs and gobs of stuff. So I'll give you a little sample of that. And like I said, at the end of the presentation, if you go download these slides, I have the URLs where all these things come from. So you can go to all the Vans Air Force pages where the creators of these things talk about them. Wire brackets and wire holders, so that this white thing here, and this complicated shaped white thing here, and the wire holders here, and this little battery box here, and this little blue wire holder here, and all these things were 3D printed. And most of them are fused filament, and that's what most hobbyists use. So here's a picture of the fused filament machine laying down one layer of filament to make this wire bracket here. Lots of fairings in RVs, so you have little things that poke out of the airplane. Excuse me. So fuel drains and things. So a lot of people 3D print little fairings to put around their fuel drains in RVs. Flat bracket fairings. So the flat bracket has a bunch of bolts and things that sticks out of it. It's kind of draggy. If you want to buy yourself some fraction of a knot, you can 3D print a fairing, put it over it. Here's an easy one. So someone 3D printed a nap pocket for their easy. So it's a rectangular container, and it slips into a little hole near the armrest, so they can put stuff in. Hinge cover for RVs. This guy had a GPS antenna right on top of the panel, and he kept making a bright reflection on the windscreen, and so he 3D printed a black cover and just put it on top of the antenna so it doesn't make a reflection anymore. 3D printed seatbelt holders for the RV-10, landing light bezel that makes the light fit snugly into the wingtip, a little clip for the edge of the step on the RV-12. Lots of people with mirrors on their RV-8s, right? So the RV-8 has most RV-8s have an arc kind of right in front of you, your passengers behind you, so it's nice to have a mirror so you can look up. So they've 3D printed little clips for the RV-8. And glare shields for their screens. This is a glare shield for a 100 or 180. Lighting mounts, all kinds of little bits of things in the cockpit that you can imagine you can 3D print. There's even a company now that will 3D print RV parts for you, including custom parts. So if you want to make a little rectangular plastic thing with your N number on it, or a tool to open the fuel cap in the RVs, that's always kind of a pain. I use my keys and it scratches it. So you can go to this website and they will 3D print RV bits for you. I think that's kind of cool. And also, even in certificated airplanes, there's a lot of things that aren't safety critical. So the FAA, lets you do a lot of interior stuff. So someone 3D printed a heating duct thing for their cub. Well, I'm not really sure it's a Piper cub. It might be one of the experimental things. And someone 3D printed a cabin heat bracket for their cub. So now the cabin heat thing sticks to this pipe over here. And apparently the Cherokee has something called a storm window latch. I'm not really familiar with Cherokees, but I know that this guy's storm window latch broke, and so he 3D printed a new one. So those are the kinds of things you can do yourselves with the small airplanes that you enjoy. So let's recap where we've gotten so far, and then we'll start talking about more ambitious and futuristic things. So where have we gone so far? When does 3D printing possibly deliver the lowest cost solution? It's when you're making relatively few of something. Because if you're making a lot of them, it makes more sense to create a mold or a tool of some kind or a form. But if you're only making one, oftentimes it makes sense to 3D print it. Or if it's unique. So if it's something that's custom shaped just for your panel that has a certain combination of things on it, or for your body shape or something, oftentimes it makes sense to 3D print it. So that applies. These characteristics apply to spacecraft, interior parts, test-related equipment like flight test stuff, mock-ups, prototypes, and tooling, and home builds. And then the other time when it often makes sense to 3D print something is when the geometry is very complex. So you don't have to machine a very complex geometry, or you don't have to build a bunch of little things that then go together. You can just 3D print the single thing with a complex shape. And just because of how much labor that saves you, even if you're going to make a whole lot of them, it makes sense to 3D print them. So that's true of the air ducts of the F-18, and it's true of the engine components in the 737 MAX and the early 350. All right, now, I'm a structures engineer, so people ask me to 3D print constructors. That's kind of the holy grail. If we could do that, that'd be pretty awesome. Why would you want to try it? You'd want to try it to lower the buy-to-fly ratio, and I'll explain what that means. It basically means you need less material. You could have highly optimized, lower weight organic shapes. I'll show you some of that too. And you could have less inventory. You could print parts on demand, right? Instead of a repair facility stocking lots and lots of spare parts, so you just have a 3D printer that prints the parts. Maybe you can do all those things. I'm not saying you can do these things, but we hope to be able to do these things, and we're working towards it, and it might be worth it. So let me tell you a little bit more about these things. So what's the buy-to-fly ratio? The buy-to-fly ratio is a ratio of how much material you buy to how much material goes flying on the airplane. And a lot of parts of, let's say you want to make this frame that's shaped like this. If you bought a rectangular block and you machined this shape out of the rectangular block, you would end up wasting 27 times as much material as go flying on the airplane, right? You would use, 4%, 3% of your material. That's really wasteful. And you say, okay, well, what if I stack 3 frames inside the block, so at least I use up more of the material? Well, you're still using, your buy-to-fly ratio is still 11.5 to 1, so you're still using less than 10% of the metal that you bought. Well, what if I make a forging that's a little bit thicker, get rid of the forging, you're still only using 1/8 of your material. And of course, if you weld stuff, then that starts getting pretty good. But welds have their own problems, as you guys know. So companies that work on 3D printed airplane parts, so they have a little bias, but they'll say that 3D printing can cut the buy-to-fly ratio of titanium parts, and they're talking about airliners, from as much as 40 to 1 to as little as 3 to 1. And the thing is, titanium's expensive. Like if you hear Boeing people talk about 3D printed metal parts, if you hear Airbus people and Lockheed people talking about 3D printed metal parts, they talk about titanium. And I'm wrong, but isn't most of the airplane aluminum? And that's true, but aluminum's pretty cheap. Buying a block of aluminum and machining out a little part out of it isn't that expensive. Buying a block of titanium and machining out a little part out of it is very expensive. So the way that 3D printing is kind of buying its way onto the airplanes right now is by allowing Boeing and Airbus and Lockheed to not have to buy big blocks of titanium anymore. So that's where the economic really makes sense, at least for now. Is this. So this is very important. This is a big part of what's really encouraging Boeing and Airbus and Lockheed and Bell and all these other companies to do research into this. So that's the vital issue. The other thing I said is you can make more optimized organic parts. Let me explain that. For those of you who haven't looked at airplane parts a lot, most of you are probably builders, but some of you may not be. Airplane parts generally look like this. So what are the kinds of features you're seeing in these airplane parts? You notice a lot of surfaces at 90 degrees to each other. You notice a lot of constant widths and constant thicknesses, or rectangular cross sections. You notice parallel flat edges. There's a lot of straight lines. There's a lot of circles. Why is that true? That's true for manufacturability, right? It's much easier to cut a thing with parallel edges and end up with a rectangle, or to drill a circular hole, or to have your whole part be the same thickness because you bought a sheet or an extrusion, than to try to sculpt curvy, funky shapes, right? These are the shapes that are easy to build. That's why you see a lot of this in the construction. But what if that went away? What if you could 3D print whatever shape you wanted, right? That a lot of this goes away. So once you design these parts, how do you optimize them? If you're a structures engineer, how do you make each of these parts as lightweight as possible? Well, you do a stress analysis. These are filaments models that are more traditionally made models. Do something here real quick. Just want to lose track of time. Just a second. All right, good. So how do you make these as light as possible? You do a stress analysis, and you figure out where the stresses are high in these materials. And ideally, if you could do anything to make these lighter, you'd always find the places where the stress is lowest and remove material from there. Like in all these parts, whatever is blue isn't really experiencing that much stress. All the dark blue stuff, you could probably shave away some material and the part will still be fine. And then as you shave away material, that region will probably increase the stress and it'll become brighter. And if you did a perfect job with this, the whole thing would be red, right? The whole thing would be seeing the same high critical stress. But you can't do that because it'll take forever. I mean, you could, but then it's going to take you, many times as long to build your airplane. So generally you don't. And the big manufacturers also don't want to spend too much time building their airplanes. But with 3D printing you can. With 3D printing you can print weird curvy shapes that don't have straight edges and rectangular cross sections, right? And the weight goes down by half if you assume the same material properties and so on, right? So that, a bunch of different companies had this little competition to see if they can reduce the weight out of these brackets. So even this bracket, if it has to take a certain load, what's the least amount of material that could take that load? We could 3D print that. And they figured out they can reduce somewhere between 40 and 70% of the weight of the bracket, which is huge. 40 to 70%. So a lot of structures engineers are salivating at the thought of being able to 3D print structure that's half the weight of current airplane structure. And there's a lot of articles and studies and PhD pieces and so on out there, right? One group said, let's take an engine pylon. So this is a jet engine pylon, right? So if you imagine the airliner wing being right here, if you imagine a jet engine hanging down here, right? They took a normal one and they said, well, what if we could 3D print any shape? They developed this shape, which has about 77% of the weight. This up here has 654 parts. This down here has 14 parts. And if you look at all the little interfaces and fasteners and little bits that you have to, assemble the part with, it went from 2,600 attachment operations to 350 attachment operations. So if you can do this, not only it's much lighter, it's much cheaper to make. That'd be great. Imagine a pedal that looks like this. This is an actual operational satellite antenna frame. So I want to give you an example of this being actually used. And there are satellites whose antennas are held up by this thing that looks like a, hip bone. These are actually made in foam. Here's some more examples. So you can go from a traditional looking airplane part to a much curvier, funkier looking airplane part. Here's the development of that satellite antenna bracket. So the original antenna bracket looked like this. The optimized antenna bracket is this. You can take a little clip like this. Something else you can do, like I showed you that Aurora jet UAV earlier, is what we call lattice structure or micro-truss structure. And like I said, if you think of it easy, right, there's foam core holding the shape of the composite laminate on the surface. Instead of foam, you get that this, this lattice on the inside. So you're basically 3D printing the foam core of the part, which is kind of interesting to do. So let's give you let's go through some specific examples. Airbus has 3D printed this bracket. They talk a lot about significant weight reduction from that bracket up here to the bracket down here. And then there's this bracket that holds various parts together, also 3D printed to be much lighter. And they're not 3D printed this bionic partition. The partition goes between the different classes in the airplane, right? So if you're sitting in a seat in an Airbus and you look ahead of you and there's that wall between you and first class, that's what this is. And they can make one now that's like half the weight of the previous one because they 3D print all the little parts inside. And just, how long ago was it? I guess it was just a few months ago, Airbus made this big deal saying we're putting the first structural 3D printed part in our airplane. On the pylon, there's a bracket on the engine pylon on the A350 that we're now going to use 3D printed titanium, probably because of by-to-5 ratio reasons. And there's news articles and they made a big deal about this, a lot of press releases and so on. Except Boeing did it first. Boeing was the first company to put a structural 3D printed metal part in an airplane. So this is the aft galley fitting for the 787. So in the back of the 787 there's the food, and there's structure that holds that galley in place. So that galley support structure is, there's quite a few articles about Boeing's partnership with a company called Norse, which is in Norway, that makes that 3D prints these titanium parts. And they've won a bunch of awards for it and so on. So right off, and used as one of those robots that deposits the metal using high energy plasma deposition. So right off the 3D printer, it looks like this. But so you still have to machine it down and smooth it, but you use much less titanium to make this than taking a block of titanium and machining it already. So Boeing's saving a lot of money on titanium by doing this. A lot of the press covers, the people who really know what they're talking about, focus on how much cheaper this is to make this way than the original one, how much money this is saving Boeing. And there's a lot of other examples too, which if you're really good at Googling, you can find a lot of other metallic structure on airplanes. So the C-17 had a panel also on the engine pylon that they have to replace in service just as it got old and corroded and fatigue cracked and stuff. And so now they're 3D printing those panels and putting them on the C-17. So there's a few flying out there. Actually, I don't think they're doing it anymore, but they did do a few. They're out there. The F-15, the pylon rib, I think the F-15 pylon is a weapons pylon or the fuel tank pylon. And there was a rib made of aluminum that kept corroding, it kept fatigue cracking, they had to keep replacing it. They said, well, why don't we just 3D print the titanium one? And once they did, it basically lasts forever. Because, primarily because they go from aluminum to titanium. And so that's been a big success story for the F-15. And there's a link that holds an engine part. I don't know if it's the engine like cowling or if it's something inside the engine, but it holds the engine on in the V-22 Osprey. Each engine has a few of these, or maybe 2 of these. And now they're 3D printing these to do repairs. And so if you look around the internet, there's a lot of information about these. So those are just some applications of 3D printed metallic airplane parts in the world. Alright, so what are the next steps? What's the future? Why don't we 3D print the whole airplane? A couple reasons. One is, like I said, 3D printing is expensive. It's not cheap. It's pretty much never going to be cheaper to 3D print something than to just get some sheet metal and make an approximation of it, which is what we do. But the main reason is safety, right? So then we get into, okay, for certificated airplanes, how do we think about safety? And for home built, it's kind of the same, except the manufacturer of the kit or whoever the designer is has to think through these same questions, right? But when it comes to certificated airliners, which is my world at work, there's FAR 25, and it does a pretty good job requiring you to think through structural safety. So it says, for example, that materials used in the airplane must have been tested. You have to have test data about the material behaviors. Any new methods of putting things together have to be tested. Fabrication operations in the factory have to be consistent. Materials have to come from specs. You can't just go out and buy whatever aluminum you want. You have to get aluminum per a certain spec, and the supplier has to meet that spec. And all the processes of making the aluminum, sheet or extrusion or whatever, and then turning it into a part, all of those have to be controlled too. And that's all required by the FAA. And, for home building, and it's not as strict, but the same mentality is there. And other parts of FAR 25 say, obviously, the structure has to be strong. Either analysis or test has to show that your airplane structure is as strong as it has to be to survive all the things the airplane might encounter, less the margin. The details have to be reliable. So basically, the FAA says, you have to know what you're doing when you're building your airplane structure. You can't just go try something and cross your fingers, especially if passengers are going to be paying to be in it. So how do you show that 3D printed structure meets all of those things? It's going to be a lot of work, right? You'd have to 3D print a lot of stuff. You'd have to test a lot of stuff. You'd have to, at some point, once you figured out a good way to 3D print stuff, kind of lock it down and say, here's what we were doing. Right? The problem with 3D printing, the problem from this point of view, is that there's a lot of people always going, ooh, I just had an idea. Ooh, we can make it a little different. Ooh, I just came up with this 3D printer. Oh, we can use this material. And from an airplane certification point of view, that's a nightmare. Right? At some point, you have to say, no, stop. Let's make it this way, which is what Norris did here. That's what Airbus did here. So you got to kind of lock it down and test the heck out of it. And once you do, you can show that it's good and put it on your airplane. Yeah, but this is hard to do. This is kind of the main challenge right now. And for example, there's who is it? ASME put together a really good video recently where this guy talks about these challenges. He says that the critical standards for how good 3D printed material has to be are still being written, but the industry needs to keep moving. There's a lot of design data. Our data comes from testing, and the data that you have to use for design is the data from whatever has been tested. And if you want more data, you need more testing. That's expensive. There's a lot of work on consistency, right? If you 3D print something, and then you try to 3D print it at the exact same thing on a colder day, or with a part arranged differently in the 3D printer, or out of slightly different material, you might get a very different part with very different properties. So you really have to figure out how to consistently 3D print the exact same thing every time. That's hard to make sense. And I really love this. Everyone wants to be second. Like everyone wants someone else to do all this hard work and then benefit from it, right? So I really appreciate that some people are trying to be first and are trying to figure this out. But it's a lot of work. It takes a long time. All right, so we're getting towards the end here. We have 15 minutes left. I'm going to geek out a little bit about why these challenges exist from materials and physics process point of view. Because again, that's really just what I do for a living. Actually, you know what? I should maybe pause here and say that one way to think about what I do for a living is I'm a fatigue analysis consultant. So if some group in an airplane company is inventing some new kind of structure, and they don't really know how it's going to fatigue you. How do you do the fatigue analysis of this weird thing? How do you do the fatigue analysis of a 3D printed part, whether it's metal or plastic? They'll come to people like the people in my group and say, how do we do a fatigue analysis of this? How do we show that this is going to last as long as we want the airplane to last? And well, sometimes it involves testing, it involves computer simulation and so on. So part of what I've done for the past 2 years is try to figure out the fatigue properties and the structural properties of 3D printed materials and 3D printed parts. So I'll show you some of that research just so you appreciate how hard it is. How challenging this is at least so I can know. So for example, let's say you have a 3D printer that puts a beam of energy on top of a powder bed, and that beam can have different energies or different speeds. So if the beam has high energy and moves relatively slowly, then sure, you're going to thoroughly melt the material, and it's going to be a nice, relatively smooth, consistent block. But if as you slowly reduce the power or increase that speed, and you want to increase the speed because you want to make more stuff per day as much as you can. You want to go fast. The material doesn't really fuse as well. So you have to find out, okay, what's the lowest power and the fastest speed that I can use in my printer and still get a solid material. And that's going to depend on how thick it is, and how hot it is today, and what exactly kind of material you have. Here's another one, right? So same 3D printer, same material. This one, they're both at 190 watts, the power of the energy beam. This one's moving at 0.8 meters per second. This one's moving at 1.3 meters per second. And the thickness of the layer went from 30 nanometers to 50. So you change a little bit, but not much, but the difference in the material is drastic. You get all kinds of pores and things in here by just changing it a little bit. So you have to find out where these edges are. What are the settings that you can use? For each printer, you have to find out what, for each printer and for each material from each supplier, you have to find out what that lowest limit is of energy, highest limit of speed, and so on. That's a lot of work. Or heat treating material, right? So, I don't know if any of you guys have any metallurgy experience, but you take a piece of steel and you put it in a high temperature oven depending on the temperature and the amount of time, you end up with very different steel. That's softer or harder or weaker or stronger or better in fatigue or worse in fatigue. So when you're 3D printing a thing by melting metal and have it coalesce and cool, depending on how you do it, you're going to get very different material properties. And here are just some graphs showing, depending on how you heat treat a piece of metal, the yield strength, which is basically the strength of the material, can vary by a lot. The elongation, so basically how stretchy it is before it breaks, can vary by a lot. So you have to keep in mind. Excuse me. All right. Now the directionality changes a lot. So if I 3D print a part and the printer is kind of going up and down like this, right? So you're kind of laying down material in this direction. It's almost like fibers in a composite laminate. If you lay down materials in this direction, you pick it up, pulling it apart this way, you're relying on the fusion of the material. Pulling it apart this way, you're actually pulling the strands of material that the 3D printer laid down. So along across the direction that the 3D printer went, it'll probably be weaker and worse in fatigue and so on than this direction. How does the strength of the material change in temperature? Here's a graph that shows that as temperature goes up, the strength goes down, and strain, like the stretchiness of it, goes up, and that's intuitive. But how much the strength goes down when it gets hotter, and how much the stretchiness goes up as it gets hotter is different for different directions. Because again, you have a bunch of material on the inside that was 3D printed. So you have to watch out for that. And failure modes, cracking, are going to be different in different directions, right? If you're pulling something, this way, perpendicular to the way it was printed, the 3D printed stuff's just going to split. But if it was 3D printed at an angle, then the fracture would progress and pull you a different way, different mechanism. You get a different amount of strength, different fatigue properties. Oh, and the scatter. The scatter is huge, right? You 3D print a thing, and you test it, and you get a number, you hear how strong it is or whatever. You try to 3D print another identical thing, and you test it, you get a pretty different number. 3D print a third one, very different number. So when you 3D print things and you go test them, for example, here they 3D printed a certain combination of polymers, and they did a fatigue test on it. And if you elongated 20% during each test cycle, one of the things they 3D printed lasted 10,000 cycles, and another thing they 3D printed lasted 1 million cycles. Right? That's a factor of 100 difference in fatigue life. So the scatter is just out of this world. And a lot of people whose job it is to figure out the properties of 3D printed materials, like me and my colleagues, you have to kind of go back to our statistics books and really think very carefully about how we deal with the fact that the data is all over the place. Because for example, you say, take the average. I don't care about the average. I care about like the worst 1% or the worst 5%, right? Imagine 3D printing an airplane spar, and I tell you, about 50% of the time, it won't break until you pull 4G. Like, you're not going to get that airplane, right? So we have to think about what the distribution is to small masses. Here's another thing. Rough surfaces are worse in fatigue. If you take a piece of material and you polish it till you're finished, it will last longer just from stress. So there are quite a few, there's quite a bit of research in academia and in the industry to figure out how do you smooth a surface without having to machine or polish all the little details, right? Can you take a 3D printed thing and put it in a corrosive chemical bath, right, that will eat away the rough surface and leave something smooth? Can you put it in a tumbler with vibrating, particles like sand or something so that the vibrating particles will smooth the surface? There are a few other ideas. But this actually works, right? So to give you a very quick introduction to fatigue here, most times you measure fatigue, you display what you measure in what we call an SN curve. So an SN curve, on the y-axis is how much you stress the thing every time, if you're doing a fatigue test like this. And the x-axis is how long it lasts, right? So if you stress it a lot, it doesn't last very long. If you stress it less, it lasts more time. And if you don't stress it very much, it can basically last forever. Anyways, that's what an SN curve is. So you can see how the rough material has this SN curve on the bottom, the dashed line, but then once you polish the surface, you have this SN curve, which means you can stress it more and it will last longer. And this really works, right? So for example, here's a 3D printed little dog bone, test specimen for fatigue. If you put it in a vibrating tumbler and it will stand, automatically smooths the surface without you having to do a lot of work, you get this. And if you do put it in a lathe and smooth it out, you get that. And here the fatigue lies. So the S-printed one is down here. The automatically fibro polished surfaces is right here. And the machine one, the one where we actually do it by hand, is up here. So, doing these automatic, chemical bath, vibrating tumbler things isn't as good as going, by hand machine the surface, but, gives you something. So there's a lot of research on this. And you can actually combine these methods too. So for example, here's one where, no surface treatment, you get that sinter all the way at the bottom, which is terrible. If you do electropolishing or chemical polishing or shot peening, which, you shoot little beads at it basically, each one improves a little bit. And then if you do multiple of these things, if you do electropolishing and shot peening, or chemical polishing and shot peening, it gets even better. So these things actually work, which is kind of cool. Yeah, so there's a lot of research going on into this kind of thing. And so the last thing I want to talk about before we start wrapping this up is there's going to be a lot of defects. And if you've worked with metallurgy, if you've worked with castings, you know that there's going to be little bubbles of air, there's going to be gaps, there's going to be all kinds of little imperfections like that. Remember, a 3D printed object is basically a giant weld, and it's going to have all the imperfections that welds have. How do you deal with that? Can you pick them up, right? When you 3D print a thing, does the QA, do the quality assurance people in your factory have some kind of sensor? Do you use ultrasounds or x-rays or magnetic, what do you do to try to find these defects? So there's a lot of work going into taking a 3D printed part and trying to find all the defects in the factory. Because once you put it in the airplane, it becomes much harder to x-ray or ultrasound or whatever.
Now let me pause the video here for just a minute. During the next part of the talk, I don't think I explained things very well, so let me give you some context here real quick, and the next bit will make a lot more sense. The idea here is the following. The larger the flaws and imperfections in your 3D printed part, the less stress it can experience in service and still hold together, all else being equal. So if you make a structural 3D printed part, you're going to want to check it for flaws using an ultrasound or CT scan X-ray machine or something like that as part of quality assurance or QA. And if that machine finds flaws in your part, then you reject the part. You don't put it on an airplane. Now, a given QA machine can only detect flaws that are a certain minimum size or larger. So even if your part passes QA, it might still have flaws. It'll just be smaller than that minimum size for that machine. Now, the smaller the flaw that your QA machine can reliably detect, the smaller the flaws that might still be in your part after it passes the QA check. And the smaller the flaws in your part, the higher the stresses your part can take and still hold up in service. And the higher the stresses your 3D printed material can take, the less material you need, which allows you to design parts that are lighter and cheaper. And that's why it's so important to develop technologies in ultrasound and X-ray, CT scans, and so on to look for flaws in structural 3D printed parts. Because the better those technologies get at finding smaller flaws, long story short, the less material is needed to make each part. So now with that context, hopefully the next part of the talk will be clearer. So here we go.
There are even companies and universities that are doing things like, okay, I'm going to 3D print this rectangle and purposely have little gaps inside it of different shapes. I'm going to try to put little square holes embedded in the middle of the material. I'm going to try to put little round holes. I'm going to try to make these of different sizes. And then once I'm done 3D printing it, I'm going to take it to my, X-ray, ultrasound, whatever it is, magnetic resonance or CAT scan or whatever, and try to see if I can find those little imperfections. And then you see some of the imperfections, and you don't see some of the imperfections. And then you wonder if the imperfections that you can't see, whether you can't see them because your QA machine isn't that great, or if maybe they just didn't get printed at all. So after you do all this, you actually have to cut this up and say, okay, what were the actual imperfections in there that I was looking for, right? So this gets really complicated, and I don't want to dive into fatigue and damage tolerance and that kind of stuff, but let's put it this way. What's the biggest imperfection, given a certain machine that you have in your airplane parts factory? So let's say you do X-rays, let's say you do ultrasound or something. For a given 3D printed part, what's the biggest imperfection that your part might miss? You kind of have to assume that an imperfection of that size is like all over the place in your parts. And that's probably where fatigue cracks are going to be pleased, if anywhere. So you have to design a part to keep your stresses low enough so that if all over your 3D printed part there are imperfections that are just too small for the people in your factory to catch, that's not going to break during the service life of your airplane. Right, so those are the kinds of things you have to worry about, is what I'm saying. And then there are metallurgists that come out and say, no, we can predict looking at the microstructure of the metal grains and how the atomic lattices are arranged, whether it's this direction or that direction, with which alloying elements, we can predict the material properties. Metallurgists are telling me this all the time. And I say, no, you can't, not really. If you take these things and you've measured how the atoms are arranged in each region of this 3D printed thing, and you test each little region, you cut out little rectangles out of each part, and break them apart, there will be some correlation between the atomic structure and the material property, but it's not perfect, it's not cut and dry. And that's, part of my job is being on the phone with metal workers to say, you don't need to do tests, you don't need to do analysis, I'll just predict it for you. And he's saying, no, I don't feel safe about that. Anyways. All right, so let's start wrapping this up. Long story short, don't believe everything you read. Right? There's a lot of companies always making press releases and putting articles on the internet and having booths at air shows and industry fairs saying, we can 3D print a wing spar, we can 3D print a fighter engine bulkhead, we can 3D print a spoiler shaped like this, we can 3D print, whatever that is. And, can you really? Probably not. You can 3D print a thing that looks like an airplane part, but is it going to, what are the fatigue properties going to be? And have you nailed the, consistency of making it the same every time? And to begin with, the first thing you ask is, does it pass like toxicity and flammability standard if it's plastic? But even if it's metal, what's the quality of that metal? And is it going to be the same every time? And no, it's not going to be the same every time. Have you thought through the statistics of how you're going to analyze it? Right? And usually the answer is no. I just made a cool thing. Right? So all the time I see websites saying, oh, we can 3D print this, we can 3D print that for airplane parts. And and I say, no, you can't. Not until you're doing all the kind of work that I'm doing. And I've even heard people from the FAA, the FAA is aware that this is happening, even for commercial airplanes. And I've heard the leaders of the FAA kind of technical experts say, we're not worried about Boeing and Airbus and Lockheed. Like, they're going to test the heck out of everything. They're not going to do anything safe. What the FAA is worried about is all these little mom and pop companies. Where people think, hey, I can just buy a 3D printer and start making and selling airplane parts. No. So, yeah, so that's part of what the scene is right now, how things are progressing. To leave you some latest, last minute, what's going on right now kind of stuff. Airbus has been testing hydraulic manifolds. So hydraulic manifolds are these insanely complicated looking things that are over there. And they connect hydraulic lines and they make the ailerons and the spoilers go up and down and that kind of thing. And just from how complicated they look, you should be able to look at it and go, yeah, that's the kind of thing you don't want to 3D print. And as they're 3D printing it, they're saving 2/3 of the weight. Which is pretty cool. And it's going to be much cheaper too. You don't have to make a bunch of little things and put together. And when you make one of those things right now, you start with a block of material, you need openings on the inside to have certain paths. So you end up drilling through the whole thing a lot to create those paths on the inside, and then plugging up half the holes that you drill. Because you just drill the hole to be able to get in there and machine away. Alright? So if you just 3D print the thing with the correct inner shape, you're going to have a single piece of material instead of plugged up holes. Which is nice. And then, Boeing once every year or two has this thing called an eco demonstrator, where Boeing gets an airplane and try to test a bunch of little technologies that reduce fuel burn or can see clearer turbulence further ahead and things like that. And they usually partner with different companies. Sometimes it's a different airplane manufacturer. And they usually publish the things that they found. So one of the things that they did this time is the 777. There's a door that opens up under the tail cone over there where the APU is, right? The little jet engine that starts up the big jet engines. And there's a little clip on the side that holds the door open. And Boeing 3D printed these organic-shaped little clips that the door attaches to. So they have fewer fasteners, they're cheaper to make, they weigh much less than the current clips. Typical 3D printing advantage. And this is the first time that Boeing used these kind of organic-shaped, weight-optimized 3D printed metal things on an airplane. But again, the F-18 has been using organic-shaped, optimized plastic air ducts for 50 years. Right? Since 2002 or 2003, the Super Hornets have had similar things to this, except they're plastic instead of metal. And if you hear people in the industry talk about the future, where are we trying to get to? One thing they'll talk about is functional integration. Right? You guys build airplane parts, first I build a structure, and then I put in the system, and then I put in the air ducts. What if we could have a structural frame that's also an air duct? What if you could have a landing gear structural part that also carries a hydraulic fluid, and so on? So airplane people are trying to figure out all this stuff we're talking about with kind of an eye on this in the future. So this company, I forget what they're called, but they're in the slides if you download the notes, partnered up with Airbus and 3D printed basically the interior of this car, engine compartment, and these weird things, these weird blobs in there, do the structural work of holding the engine, and carry fluids, and do the cooling, and store liquids like brake fluid and windshield wiper fluid, and that kind of thing. And they have all the load bearing and crash worthiness requirements that the car engine mount has to have. So that's kind of what we're hoping to get to with airplane. That's obviously pretty fun in the future. All right, to wrap it up. For you guys, what's coming for us? What's coming for us home builders? There's a company called Desktop Metal that's trying to make a relatively small and affordable metal 3D printer, so you can 3D print metal parts. And there's another one called Virtual Foundry, so it's these two in quotes here. And the way most of them work is they lay down a filament, and the filament is basically metal powder inside a plastic or resin, stuff goo. And then once it lays out all that stuff, you put it in a furnace, and all the plastic stuff burns away, and you're left with the metal. So of course there's going to be some porosity, some imperfections, but you do have a metal part, and they're working on making those be fewer pores and imperfections. So that's kind of cool. There are filament 3D printing machines that are working on having carbon fiber filament. So as you're putting down your molten plastic one layer at a time, if you wind a little carbon fiber through it, you can basically 3D print carbon fiber. And that's actually kind of how the big manufacturers 3D print or make a carbon fiber part. Right? They're putting on carbon fiber tape one layer at a time. So in a way, we're getting towards being able to do that at home. And as you might expect, the 3D printed plastic with carbon fiber, which is the red line there, is much stronger and much stiffer than just plastic, obviously. They've already tested some of it. And if you're thinking of maybe trying to get into this, maybe there's some things in my home built on the airplane I already have, or my Cessna, that you might benefit from it. The EAA has a great series of webinars. Hopefully you guys know about it. And one of them is called 3D Printing for Experimental Aircraft Builders. The link to this is in the slides if you download it. And the guy who does it is Scott, what's his name, Vandervee? Is that right? He's a guy who teaches a composite workshop right here. He's right here right now. He's great. He's very knowledgeable. He's actually done all this kind of stuff for airplanes. So go watch Scott's video. And it's, he goes through how I open up, which piece of software do I design the part in, how I design the part, okay, here's the printer, how do I make this part print the right way. It's really great step-by-step introduction to how you would actually do this for a home build. And I finished 1 minute early. Are there any questions? Of course, I'm happy to hang out and answer questions afterwards. Yes. Yeah. So how do you develop the parts? Yeah, you use CAD. You have to some kind of computer-aided design. So there's multiple steps. First, you have the computer-aided design, and you define the shape, and then there's a piece of software that says, okay, given the shape, what should the path of the 3D printer be to make layers of material that will create that part? And then that is what you send to the 3D printer. But yes, Scott goes over that in the video. Yes, any other? Yes? Why do you use titanium instead of aluminum? Because titanium is expensive. So if you 3D print titanium, you save a lot of material, which means you save a lot of money. If you 3D print aluminum parts, you save a lot of material. They didn't really save that much money, so you might as well just keep making aluminum parts the way you're making them. And that's not really, I'm not saying that's absolutely true. There's a lot of research going into 3D printing aluminum too, but the thing is 3D printing titanium pays for itself much more easily. Because right away, as soon as you figure out how to make something out of titanium, you're saving a bunch of money because you're not having to buy blocks of titanium and machine parts now. So you're trying to get away from having to buy blocks of titanium, just because titanium is expensive. Aluminum's relatively cheap. Yes, yeah, and it's strong, right? It's like the F-15 pylon rib, they went from an aluminum rib to a 3D printed titanium rib, which is now stronger and lasts forever, rather than the aluminum ones that were falling apart. Yes?
Use of plasma metal deposition. Do they ever heat treat that afterwards?
Ah, yes. Do you heat treat the parts afterwards?
To try to...
You do a couple of things. One, you heat treat it to kind of stress relieve and make sure you get the alloy you want. What most 3D printed metal parts also do is what we call hot isostatic pressing. So you put it in a high pressure chamber that kind of heats up the metal to make it a little softer, and then squeezes it so that the imperfections and the gaps inside get smaller. So yeah, most 3D printed metal parts go through hot isostatic pressure or HIP. Yeah. Any other questions? Yes? What's that? Do I see it becoming a high volume manufacturing technology? For very complex shapes, I absolutely do. Like right away, it's going to be easier to 3D print that kind of thing in high volume than making it using a bunch of drilling and machine operations. And the classic example is the engine nozzle on the 737 MAX, right? GE, remember, Boeing makes about 2 737s a day, more than 2, and each engine has 19 of these fuel nozzles. So GE has to make like, did I go? Yeah, there it is. So GE has to make like 80 of these things per day. Not yet, because Boeing's still making the old 737. But anyway, GE has to make a lot of these per day, and they're 3D printing them. And they have a lot of 3D printers making a whole bunch of these every day. And there's more examples too. Yeah? Uh-huh. So question is, metallurgists care about metal grains, and basically it's how the atomic lattice structure is oriented within each grain of the metal. Because if you look up at metal, if you zoom into metal, you see lots of little grains, and within each grain you have a crystal in a different orientation. What does 3D printing do for that? The answer is, it's a giant mess. Again, it's like a weld. You have little bits of material with atoms arranged every which way. Some places you have small grains, some places you have large grains. And as the material cools down, the thicker regions, which are cooling down more slowly, are going to have more time to line up their atoms and make bigger grains, while on the surface around thin parts, they cool more quickly, it kind of gets frozen in place, so you have more of a mess, and it depends on the temperature, it depends on all kinds of things. And so, yeah, part of the research is 3D printing pieces of metal, and doing this, I didn't really explain what this is, but the different colors correspond to different atomic arrangements in the grains, and then trying to see if you can predict material properties from the known grain orientations. And yeah, my takeaway is that it's kind of a giant mess, and if you lock down a process and test the heck out of it, you can kind of feel good about it. But if you just try to go to the atomic level and look at what the grains are doing and predict behavior out of that, it might be possible. Right now, it's kind of tricky at best. But there's definitely a lot of people working on it. Yes? And pretty soon I'm going to have to leave it. So last question, and then I'm going to shut this off here. Of course, you guys can come talk to me if you want. Yeah? Okay, so what do you recommend companies like for you to buy parts from, or for you to work with? Or? Well, like I said, Boeing partnered up with Norris. They made some really huge advancements in 3D printing. Norris is basically responsible for figuring out that aft galley situation. So that's very impressive. And so that's in Norway. And I showed you a couple of 3D printing manufacturers that are trying to build stuff for home. So there's Desktop Metal and Virtual Foundry. So you can try to look into those. All right, that's it. I better. Oh, wait, one last thing. My website is understandingairplanes.com. There's a resources tab. I'm not going to get back here. Understandingairplanes.com. There's a resources tab where you can download all my slides, all my other slides about airplane design and everything, email me and whatever. So, right, that's it. Thank you.